In this video, I'll introduce you to some important derivative rules and show how they're applied in a few examples. First up, the sum rule. To find the derivative of the sum of two functions, f of x plus g, we'll consider the difference quotient. When we write out the difference quotient and consider simplifying, I see that in the numerator, I can rearrange the terms so that f of x plus h is subtracting f of x, and g of x plus h is subtracting g of x. Then when I distribute the limit, I see that I'm just looking at the sum of the derivatives of f and g. So the derivative of a sum is simply the sum of the derivatives. It's that simple. Meanwhile, if I were to consider the difference rule, changing these plus signs to minus signs, I see a similar result. That is to say that the derivative of a difference is equal to the difference of the derivatives. However, not every derivative rule is quite so simple. Here we'll look at the product rule, the derivative of a product of two functions, f times g. When I set up the difference quotient, I notice that I'll have to do a little more work in order to simplify. That work involves the oldest trick in the book, which is adding 0. So right here, you can see that I've subtracted f of x plus h times g of x, and then I added it back in. So I did not change the numerator at all. I changed the way it looked, but I didn't change its value. And now it's set up to do a little factoring by grouping. Among the first two terms, I'll factor out an f of x plus h. Among the second two terms, I'll factor out a g of x. And now what I see is that I'm looking at a limit of f times g's derivative plus g times f's derivative. And that is the derivative rule for a product. It's called the product rule. F of x multiplied by g prime plus g of x multiplied by f prime. That's the product rule for derivatives. You'll use it a lot. The last rule we'll look at today is called the quotient rule, the derivative of f divided by g, assuming g of x is non-zero. We set it up with the difference quotient, rewrite it as 1 over h like we often do, and now find a common denominator. So the common denominator will just be g of x plus h multiplied by g of x. When I rewrite over the common denominator, I'll now try the same technique that worked for the product rule, and that's adding 0. This time I'll subtract f times g and then add f times g right back in. That adding 0 is, with regard to proofs, one of the oldest tricks in the book. That creates a nice factoring by grouping problem. Those two terms in blue there have a common factor, and the two terms in yellow have a common factor. The blue terms, I'll pull out a g of x, and for the yellow terms, I'll pull out a minus f of x. And now you can see structurally where the quotient rule comes from. I see g of x multiplied by f of x plus h minus f of x over h. That's f's derivative. And then I have minus f of x multiplied by g of x plus h minus g of x over h. That's g's derivative, and everything is over g times g. And this is the quotient. And that's a little Cab Calloway played because sometimes to memorize the quotient rule, we think of it as low d high minus high d low all over low low. Handy little mnemonic to remember g times f prime minus f times g prime over g squared. Let's look at some of these derivative rules in an example. Find the derivative of f of x equals sine of x over 3x squared. Over here, I'll keep some helpful tips, including the power rule, the product rule, the quotient rule, and the derivative of sine x, just so we have them handy so we can use them to find this more complicated derivative. Now, since this function, sine x divided by 3x squared, presents itself as a quotient, I'll use the quotient rule. So in case you missed that Cab Calloway reference earlier, the g times f prime minus f times g prime over g squared can be memorized using low d high minus high d low all over low, low. And low here represents denominator, high represents numerator. And so the derivative will be 3x squared, that's the denominator, multiplied by the derivative of the numerator, which should be the derivative of sine, and that's cosine, minus high, and that's sine, times the derivative of the denominator, and that's 6x. And it's all divided by low, low, which means 3x squared multiplied by 3x squared. Or if we simplify it a little tiny bit, we would get 3x squared cosine x minus 6x times sine x over 9x to the fourth. One simplification that I tend to do is if there's ever trig functions involved, maybe multiplied by polynomials, it's nice to put the polynomials first so they don't get mixed up in the argument of the trig function. You can continue to simplify here if you want to take 3x squared cosine and divide by 9x to the fourth, and then subtract 6x sine x over 9x to the fourth, though it's not really going to simplify the function a whole lot. Let's look at that example one more time, but this time I'm going to change it up a little bit. What I'm going to do is I'm going to rewrite the function. Initially, this would be called a strategy known as look before you leap. Can you simplify the function a little bit in such a way that maybe it's going to make taking the derivative a little easier? Here, I'll rewrite it as 1/3 x to the negative 2 multiplied by sine of x. Now, the reason I might want to write it like that is now it's written as a product, and I can use the product rule instead. And the product rule is a little simpler than the quotient rule. The product rule follows the structure f times g prime plus g times f prime. So in this case, f is 1/3 x to the negative 2, and g is sine of x. So that tells me that my derivative will be 1/3 x to the negative 2 multiplied by cosine of x plus sine of x multiplied by negative 2/3 x to the negative 3. I'm just using the power rule on 1/3 x to the negative 2 there. And here, once again, I can simplify kind of as much as you'd like. The first term, 1/3 x to the negative 2 cosine x, could be rewritten as cosine of x over 3x squared. And then the second term, sine of x times negative 2/3 x to the negative 3, can be rewritten as negative 2 sine of x divided by 3x cubed. And you'll notice that this derivative doesn't look exactly like the derivative that we got when we used the quotient rule. And it comes down to simplification. As you can see here, if I were to take the derivative that I found using the quotient rule and do the division on each term, the simplification would work out to be exactly the same. So it's really a matter of preference for certain problems, whether you use a product rule or quotient rule. But you need to know both rules because there are certain problems that could only be done one way. One thing that I found useful when I was learning the product rule and the quotient rule for the first time is often look to see if there's multiple ways that you can find derivatives. If you could do it two different ways and see that your two answers are the same, then that's a good way to know that you're using the rule correctly. Here's an example. Say I was asked to find the derivative of f of x equals 3x minus 1 times 2x plus 5. So 3x minus 1 is my first function, and 2x plus 5 is my second function. And therefore, using the product rule, I would say that the derivative is going to be the first function, 3x minus 1, multiplied by the derivative of the second, and the derivative of 2x plus 5 is 2, plus the second function, which is 2x plus 5, multiplied by the derivative of the first. The derivative of 3x minus 1 is just 3. So then I distribute my 2 to get 6x minus 2, and I distribute my 3 to get 6x plus 15. And collecting the like terms, I get my derivative 12x plus 13. However, I'm sure you noticed in the very beginning, I could have multiplied these two binomials to get 6x squared minus 2x plus 15x minus 5, and collected those like terms to get a 13x, and just taken the derivative using the power rule of 6x squared to get the 12x, and the 13, positive 13x to get 13. So now I can see that the derivative worked both ways, both with the product rule and with the power rule. Let's see another example. Perhaps somewhere along the way, and if not, maybe in the future, you'll have a teacher that'll say, hey, you need to memorize that the derivative of tangent x is equal to secant squared. Maybe you'll have to memorize all sorts of other derivatives as well. But we can see that the derivative of tangent of x is secant squared using our power rule. If y is equal to tan x, then y is equal to sine over cosine. And if I use my handy quotient rule, I can see that the derivative is going to be low, which is cosine, multiplied by the derivative of sine, which is also cosine, minus sine, multiplied by the derivative of cosine, which is negative sine, all over low squared, which is going to be cosine squared. And you'll notice in that numerator, perhaps for the last time this year, we see that very, very common trig identity, cosine squared plus sine squared, which of course we know to be equal to 1. And if there's a 1 in the numerator and a cosine squared in the denominator, that tells us, using the quotient rule, that the derivative of tangent is secant squared. So as you can see, the sum, difference, product, and quotient rules are really handy. Hope this video helped explain them. See you next time.